All right, now we're getting into geometric optics. Let's talk about images. So we have two different types of images, and you should have seen it already, some in the labs that we've done. The first one is a real image. And with a real image, it actually shows up. It forms where light rays cross. So this would be like when you guys did it with the concave mirror. You saw that those rays reflected off of it and came back together. Whereas with your convex mirror, with the convex mirror, you got a virtual image. And with a virtual image, you saw that the rays diverged. They spread out, and that if you drew the lines, the dotted lines backward behind where you saw those images coming from, or where your brain interprets them as coming from, that's where you would get an image. So let's look at how those show up. How do we get an image with a concave or a convex mirror with light coming from infinity? So like with the sun, it's far enough away that only the light that's traveling perfectly parallel will reach the Earth. So we know all the light rays, if they come from infinity, are coming in parallel. So first thing I'm going to do, I'm going to draw what we call the principal axis. So that is the line that goes through the center of your lens or your mirror. And for here, this is a converging, so a concave mirror. And I'll draw it like that. It doesn't have to be perfect. I should probably make it a little better. But as long as your math works out pretty well, you're going to be fine whether or not you get a good looking mirror when you draw it. Okay, if I have rays that are coming in from infinity, every mirror has what's called a focal point. So the focal point is where light rays that come in parallel to the principal axis, this guy right here, principal axis, light rays that come in parallel to that will always be reflected through the focus. The focus is represented by a capital F. And then beyond it, at 2F, we have something called the center of curvature. We'll talk about that more later. But I'm just going to draw a couple of rays that come in from infinity, so parallel to the principal axis. When they get to the mirror, I'm going to stop. I'm going to turn this around. And again, you may want to be using a ruler for this. It makes it a lot easier than trying to draw straight lines. I'll just do a couple of different ones. If I were to do the one directly through the principal axis, if I had a ray directly on that, then it would go just straight back when it hits the mirror. It's basically behaving like a flat plane mirror then. I'll draw one more just for good measure. But you should see that all of those rays come together at the focus. Knowing where the focus is important for some of the equations that we're going to do later, and we'll figure out how to determine that for really far away objects. So right here is our focal point. The distance from the mirror to that is represented by a lowercase f, and that is our focal length. All right, now, how do we do the same thing for a diverging lens? Well, I'll draw my principal axis real quick. And then, in this case, since it's convex, I'm going to make the mirror curve the opposite direction. My focal length this time is now behind the mirror. So I'd put one right about here. My center of curvature would be over here. I don't need it for this problem right now. Focal point. All right, so I'll draw a couple rays in. This is where it gets a little bit different. When the ray comes in parallel to the principal axis, I remember before I was aiming through the focus, but now these rays get reflected back. The reflective side's over here. So what I'm going to do is I'm going to aim at the focus. I'm going to have a ray shoot off of it going this way, and then I'm going to draw dotted lines backwards towards the focal point, showing that's where your brain would interpret the rays as coming from. So I'll do a few more here, just so you can get the idea of how it's supposed to work. This one reflects, it's on the lower half. I should aim through my focal point. So I've got my meter stick. In your case, your ruler is going to be lined up with your focus. I'll draw my ray off and then the dotted line backwards through here. So eventually when we start looking, right now we're not getting an image, but eventually if we have rays that are not coming from infinity, we should be able to find the location of our image and its height and its magnification and its orientation, all that fun stuff. So this would be a diverging lens. Notice these rays all come back together at the focus. These rays all spread out away from the focus, thus converging and diverging. All right, so now how do we determine the focal length of a concave mirror? First thing we have to do is we have to point the mirror at an object far away. How do we determine what far is? Well, it has to have a distance that is significantly larger than its center of curvature. So D significantly bigger than C. Then the image will form at the focus. In real life, it won't actually be at the focus. It'll be pretty close, but it's close enough that it works for your answer. All right, next thing over here is our mirror formulae. This one is going to be how we determine where the location of the image shows up. So little f represents your focal length. SI is the distance to your image, and SO is the distance to your object. They changed it since I've been in physics. It was DO and DI, and it made a lot more sense, but I guess you use D too often in physics, so they had to change it. And then over here, magnification. This is how big the object is compared to the image is compared to the object. That's going to be the height of the image over the height of the object, or the negative of the distance to the image over the distance to the object. That negative sign is important because it's going to tell you about the orientation. So if I have a magnification where it's negative, that means it's flipped upside down. So let's take a look over here. Here are our definitions of the different variables. Focal length is positive when we have a concave mirror, and it's negative when we have a convex mirror. Just like we saw before, our focal length on the positive side, same side as the object, here on the opposite side of the object, and so it's going to be negative. Our object distance is always going to be positive because that's just how we define it. It's the side that it's on, and then it's never negative. Our image distance is going to be positive when it is a real image, and it's going to be negative when it's a virtual. Because with a real one, you can have actual light rays show up, form together right here. Whereas when we have a virtual, it shows up behind the mirror on the opposite side of the object. For magnification, it's going to be positive when we have an upright image, meaning that the orientation of our object is the same as our image. For instance, if my object was above the principal axis, like over here, let's say I had an object above, the image of it would form above the principal axis as well. If it's negative, then we have an inverted image where it'll be upside down. And you'll probably have seen some of that already in the lab. Your object height is always going to be positive because we can flip the principal axis. So that way we always end up with it on the upside. Realistically, it could be either, but basically in every problem, it's always going to be on the top. So we'll never have your object upside down. Your image height, if it's positive, you have an upright image. And if you have a negative, then it's going to be inverted. Which hopefully you can see how that works based on the equations over here. One thing to take into account too with magnification, if you end up with a number that's bigger than 1, it's going to be larger. Smaller than 1, then it's smaller. And if it's exactly 1, it's the exact same size. All right, finally, this is some stuff that you should have seen in the lab. This is where we determine where the images should show up based on where you place them and with what type of mirror. These first 1, 2, 3, 4, 5 ones up here, these ones all represent with a concave mirror, whereas for convex, it doesn't matter the location. So when you have an image that is an object that's beyond C, your image is going to show up between C and F. Whereas if you have one exactly at the center of curvature, this is something we talk about. If you go through the center of curvature, you just come straight back through the center of curvature. So that one is going to be at C. The image shows up at the same place as the object. When you're between C and F, this one is going to give you something where it is beyond C. Whereas when you're at the focal point, parallel rays that come in will go to the focus. So rays that come from the focus come back parallel. If you have parallel rays, they never connect, so you get no image. Finally, if you're between the focal point and the mirror, what you end up with is an image that is behind the mirror. And that's true of any location with a convex mirror. All the time, you'll end up with them behind the mirror. And so now let's describe what the images look like. When you are beyond any object that is beyond the focal point for a concave mirror is always going to be real. So for these first three, real, real, real. No image here, so we can just kind of cross that out. Anything that's behind the mirror is always going to be virtual. All right, now the next descriptor, we're going to be looking at whether it is inverted or upright. So anytime you get a real image, definitionally, because the rays are crossing for you to make it, it's going to have to be inverted. That's what flips it upside down. Real images are always inverted, which means that virtual, on the other hand, have to be upright. Now, the easiest one of these to remember is the center of curvature, because if you go through the center of curvature, you go in and come out exactly the same size, just on the opposite side of the principal axis. So on this one, we should end up with something that's the same size. Our last category here is size. Now, on this one, you go from far away to being really close. And as a result, you get a lot smaller because the image is closer to the mirror than the object, which makes it look tinier. Now here, we're really close to the mirror, and our image shows up further away. That's going to make it larger. Now on the last two, you can think of this one as kind of like looking in a spoon. When you look into a spoon, you get your face all stretched out, and so you get a larger image. You can also do the math, and you can see it works out. Some of you guys like to do this mathematically. Some of you like to understand it conceptually. If you want to do the math, you should always end up with an object distance that is smaller than your image distance. And so it's going to end up larger. Whereas with this last one, no matter where you put an object with a convex mirror, this is like looking on the back side of a spoon, you're always going to look super tiny. This is like those mirrors that are on the top of the gas station where they've got the bubble so they can see more of it. Everything on it is smaller so that they can see you. And so as a result, we end up with a smaller image here. So number 7, in general, for concave mirrors, as your object moves from the mirror towards infinity, and this is up until you get to the focal point, so until F, your image distance will increase. So as the object gets closer to the mirror, the image moves further away until you get to the focal point.